All right, so today I want to just address some of the key points from Module 1, uh, things that you should all be taking away, whether you've already finished it or whether you're still working on it. I just want to highlight a few things. Um, I would say the first one is the octet rule is super important. Super duper important. So you never want to go over the octet, which means you never want to see 5 pairs of electrons or 6 pairs of electrons around an atom. So these things, like carbon with 5 bonds, or oxygen with 2 bonds and 3 lone pairs, uh, or nitrogen with 4 bonds and a lone pair. These are all big, big no-nos. We even have a special name for things that go over an octet like that. We call this a Texas carbon or a Texas oxygen, because everything's bigger in Texas, I think. Or because Texas is the lone star state and they've got a 5 pointed star, like this carbon here in the middle kind of looks like a 5 pointed star, like the Cowboys logo. But Texas carbons don't exist. So if you ever find yourself drawing them, you want to immediately correct yourself. Um, and then I'd say the second part of that is occasionally we will go under the octet, but it's rare. All right. So second part of saying the octet rule is super important is to say only go under an octet if you have no other choice. And there's two main examples where you'll see that happen. Carbon that has 3 bonds, no lone pair, and a positive formal charge. Or boron that has 3 bonds and no lone pairs. But boron in that situation is neutral. And then there's one really rare example that we call a carbene, that when it comes up later in the year, like I'll make a big deal about how weird it is. So at this point, you shouldn't expect to see this. But I do, like, for completeness, want to point out, all right, we will see one other example down the road called a carbene. And that example is a carbon that has 2 bonds and a lone pair. So carbene is very rare. I'll warn you when that's going to come up. These other two examples, this one we call a carbocation. Any idea where that name might come from? It's carbon and it's a positive ion. Name for a positive ion is cation. So carbocation, not carbocation. So we will see carbocations in the middle of reactions, but they're still not that common. So if you find yourself drawing a carbocation, you want to ask yourself, is there another way I could draw this that follows the octet rule? And carbocations are not stable. So I'm going to give an example from one of the skill checkers. Which was H2COH plus. And I'd say the structure that the majority of people drew was that. And if you drew that, what I wrote was, all right, this is one possibility for that chemical formula. But there is a more stable one. There is a way to draw this molecule so that it follows the octet rule. So this is a molecule that has a carbocation, but I want to think about, all right, how could I make this follow the octet rule instead? Well, who's breaking the octet right now? Carbon, right? Carbon only has 6 electrons around it. And since carbon only has 6 electrons around it, it's the one that needs 2 more electrons. So how could I get carbon 2 more electrons to follow the octet rule without making anyone else break the octet rule? Gibbs? Aha. We could notice that oxygen over here has this lone pair. And this lone pair, has 2 lone pairs. But it could decide, instead of just holding on to the lone pair by itself, it could say, oh, look at poor carbon next door. Carbon doesn't have a full octet. And isn't it selfish of me to just hold on to these 2 electrons by myself and not share them with my neighbor who's in need? And so what we can imagine happening is oxygen deciding to take these 2 electrons and say, all right, I'm going to pitch those into the middle. I'm going to share them. And by sharing them, carbon's now going to have 2, 4, 6, 8 electrons around it. So carbon follows the octet rule. Oxygen still follows the octet rule. So actually, I'm going to draw in numbers to count the electrons. So for carbon, it's got 2, 4, 6, 8 electrons. 4 pairs of electrons around it for the octet rule. And for oxygen, it's got 2, 4, 6, 8 electrons around it. So it follows the octet rule. All right. So both atoms follow the octet rule here. Whereas here, carbon breaks the octet rule. because carbon only has 2, 4, 6 electrons around it. And I think one point of confusion for some people was when you're counting in terms of the octet rule, shared electrons and lone pairs count the same. They count equally when you're counting for the octet rule. Whereas for formal charge, which I'll talk more about in a minute, for formal charge, shared electrons and unshared electrons are counted differently. And I think that was a point of confusion. All right. So my structure on the right follows the octet rule. But how I got there was oxygen decided to take 2 of its own personal electrons and share them with carbon. Well, that's got to have some consequence. What's the consequence of oxygen deciding to share that pair of electrons with carbon instead of owning it itself? It's sort of, quote, missing an electron now, so it has a positive formal charge. Yeah. So oxygen now has the positive formal charge. Notice our chemical formula had a +1 total charge. So when I add up the formal charges, they should add up to +1. And they do. So it turns out this structure on the right is more stable than the structure on the left, because the structure on the right follows the octet rule. All right, so the first key point I wanted to make today was octet rule. Super important. Don't ever go over it. There is one exception I'm going to show you with phosphorus. Like, maybe you'll get there by the end of the year, but it's a really weird reaction. But never with carbon or nitrogen or oxygen. So never go over the octet. And only go under the octet if you absolutely have to, and it's really only ever going to be carbon or boron that does that. I guess aluminum, but we'll introduce that when it comes up. Aluminum's a lot like boron, so I guess I could change this to say 3 if I want to be complete. And I want you to get to the point where if you draw a structure that breaks the octet rule, it kind of hurts a little, like there's a little alarm bell that goes off when you see it, so that you will become physically unable to draw structures that go over an octet. The other thing I'll point out is we're never going to see odd numbers of electrons. They do exist, and I might put together an optional module on those kind of structures. They're called radicals. But I guess the third point about the octet rule is don't leave electrons unpaired. So for instance, I saw a drawing that looks like this for C2H4. And if you have a drawing that looks like that for C2H4, now you've got these 2 unpaired electrons, which means anytime there's an unpaired electron, automatically you're breaking the octet rule, because if you have an odd number of electrons around an atom, it can't be 8. If I were to count up electrons around this carbon, it would be 2, 4, 6, 7. And around the other carbon, it would be 2, 4, 6, 7. So in this case, the solution might seem fairly straightforward. How could we make this follow the octet rule? Chris? Put a double bond between the carbons. Take those 2 lonely electrons and just make them shared in between the 2. So this over here is definitely wrong structure. It would be better to take those 2 lonely electrons and pair them up and share them between the 2 atoms. So if you find yourself drawing unpaired electrons, it's a mistake. Not to say that that doesn't ever happen, but the vast majority of the reactions we'll study, well, all the reactions we study, unless anyone really wants to study radical reactions, we'll deal with pairs of electrons, never unpaired ones. All right, are there any questions about the octet rule? Yep. So the question is, what about lone pairs? So lone pairs are fine because they're pairs. So you should always, if you're drawing one dot, there should always be another one next to it. Yeah. So lines represent 2 electrons, and then dots represent 1 electron. But what I'm saying is, if you have 1 dot, there should always be 2 dots. If you have 3 dots, there must be a 4th. Should always be pairs. All right, so second thing I wanted to address was formal charge. Formal charge and patterns that we see in formal charge. On the periodic table I gave you. Actually, I'm going to pull one out so I can make sure I get the right information. All right. So in the top right corner of each box, just as kind of a guide to help you, I put in common formal charges. I put that there just as kind of a helpful reminder of things you should expect to see and things you shouldn't ever expect to see. So if you ever find yourself putting in a formal charge that's not listed there, it's probably a mistake. And while you should know the rules for finding the formal charge on any atom, it's also helpful to just recognize patterns. Like once you practice this enough, you want to recognize the patterns. So you want to know, what does carbon look like when it has 0 formal charge? What does it look like when it has a +1 formal charge? What does it look like when it's -1? So if we look at patterns for carbon, if it's going to have 0 formal charge, what does it look like? Four bonds, yeah. And it could be 4 single bonds. It could be, carbon with double bond and 2 single bonds. Could be carbon with 2 double bonds. So anytime it has 4 bonds, 0 formal charge. When would it have a positive formal charge? We've already seen that one. 3 bonds, yep. So 3 bonds, and the key there is no lone pairs. LPs we'll use as an abbreviation for lone pairs. If you talk to your parents about LPs, they probably mean something different by it. Or actually, hipsters too might talk about LPs, like records. And then, how would I get carbon with a negative formal charge? Well, one way would be 5 carbons, make it a Texas carbon, but we're never ever going to see that. So it wouldn't be a, that's not what's representing this -1 formal charge. 3 bonds in a lone pair. So 3 bonds in a lone pair, that's what gives it a negative formal charge. So you shouldn't ever expect to see carbon do something other than one of these patterns. Let's do that for one more element. Oh, I don't have my cards out. Caroline, pick an element. One that we use a lot. Nitrogen. All right, so let's do the same thing for nitrogen. Try and draw for yourself. So for nitrogen, it's listed as 0, +1, and -1 are the common formal charges. Try and draw for yourself what nitrogen with 0 formal charge looks like, what nitrogen with +1 looks like, what nitrogen with -1 looks like. All right, what does nitrogen with zero formal charge look like? Three bonds and a lone pair. What does nitrogen with a positive formal charge look like? Four bonds. And nitrogen with a minus one formal charge? Two bonds and two lone pairs. Tova. Yep, you could also have double bonds. So for zero formal charge, you could have nitrogen with a double bond, a single bond, and a lone pair. You could have nitrogen with a triple bond and a lone pair. Those both work. Here you could have nitrogen with two double bonds and a positive charge. Nitrogen with a double bond and two single bonds and a positive charge. Nitrogen with a triple bond and a single bond and a positive charge. Yep. So multiple bonds work as well. So the reason we practice these is we want to get to the point where this becomes kind of second nature and it just feels right to have nitrogen with three bonds and a lone pair. And when you see nitrogen with four bonds, you immediately think, oh, wait, that's a positive formal charge. When you see nitrogen with just two bonds and two lone pairs, now you think, oh, yep, that's a negative one. And really, like any other skill, it's a matter of practice. So you should be able to actually do this for any of the elements listed here, particularly the ones on the right. Don't worry about the metals on the left-hand side. But for any of those elements on the right-hand side of the periodic table, you should be able to go through this pattern for yourself. All right, questions about formal charge? All right, so then the last thing I wanted to talk about was comparing structures. And for comparing structures, really, it's about knowing what order the factors, what order we want to consider the factors. Like, what's more important than what? So, I would say these are rules from most important to least. And the first key rule is, I started with it, octet rule. So if a structure follows octet, it's more stable than one that doesn't. And while you can just kind of remember that as a rule of thumb, if you want to think of a more fundamental way to explain that to yourself, I'll go back to that example we did earlier when we were comparing these two structures. We know that electrons have what kind of charge? negative. So what kind of charge do they like to be around? Positive. So if you ask this lone pair on oxygen here, would you rather just hang around oxygen's nucleus? You know, you get to be around something positive. Or would you rather hang out between two positive nuclei? Those electrons, every time are going to say, oh, I'd rather be between two, right? There's no doubt that electrons would rather be shared if they can. It's just they can only be shared up to the octet rule, and then there's no more space. So as long as there's space, try and fill it in by sharing electrons. That's what that first rule is. Then, if you're comparing two structures and they both follow the octet rule, or they both don't follow the octet rule, then you go on to the second thing, and that is minimal formal charges is better. And most people seem to get this rule. So if you have one structure, no formal charges, another structure with positives and negatives, the one with no formal charges is going to be more stable. And there you can think of it as when you have positive and negative formal charges that are separated, you're keeping apart two things that are attracted to each other. And so if you're going to keep apart two things that are attracted, you know, that's going to be a less stable situation than when you let them come together. And then the last rule is if you're comparing two structures and they both have the same number of formal charges, then you consider our main measure of the personality of an atom. Going back to the periodic table, here I gave the little example. What's the most important number in the box? Down here, electronegativity. So electronegativity tells us how strongly an atom pulls on electrons. Those numbers are going to be really important to us in this class. That's why I put them on your periodic table, because you want to use that to get a sense of what's the personality of that element. Carbon at 2.55 is kind of in the middle of the scale, which means not too strong, not too weak. You look at the periodic table, nitrogen's 3.04. That's quite a bit higher. So nitrogen is a little more of a bully, a little more pulling on the electrons. Oxygen, 3.44. Now we're getting high. You know, that's the second highest electronegativity value. So that's really a bully, really pulling on electrons strongly. So if we think about where our formal charges are in atoms, would a negative charge like to be with something that pulls on electrons or something that doesn't pull on electrons? Well, what kind of charge do electrons have? Negative. So more electronegative atoms are going to pull the negative charge towards themselves. So negative charges prefer to be on more electronegative atoms. And I'll abbreviate electronegativity a lot as just E with a negative sign, neg. Sometimes we'll just use En, capital En, equals electronegativity. Because it's 17 letters, it's a long word. I did teach autocorrect on my phone to recognize electronegativity, so that was nice. because sometimes I need to like write it into stuff. Yep. All right. So electronegativity is how strongly that atom is pulling on electrons. So atoms that pull more strongly on electrons are more likely to get if the excess of electrons. A negative formal charge indicates extra electrons in that part of the molecule. So more electronegative atoms are more likely to pull the extra electrons to themselves. And then the opposite is also true. Since more electronegative atoms pull more strongly on electrons, they're less likely to take on a positive formal charge. You know, I think of them as getting really angry when they have to take on a positive formal charge. Like oxygen gets a positive formal charge and it's kind of pissed off. It's like, I'm oxygen. How dare you do this to me? Whereas nitrogen, you know, is a little less angry to have the positive formal charge. So positive formal charges prefer to be on less electronegative atoms. Would one of them be more stable? You mean, would one of these rules be more important than the other? You won't find yourself in a situation where you're comparing one molecule with a negative to one molecule with a positive, because then they have different chemical formulas. And here we're talking about comparing structures with the same chemical formula. So that's why I list this third one as just one rule, because you're never going to have a conflict there. All right, so those were my key points from the first module. Any lingering questions from the first module? All right, I will post those notes online.